Lab 5, Motion of Falling Objects, Physics 2211, Section N. The goals of this lab. The primary goal of this lab is to expound upon the impact of gravity on a falling object using Newton's second law of motion. Also, we intend to explore the impact of the drag force on two different massed falling objects. Lastly, we want to determine the correlation between objects of different masses reaching terminal velocity. As in several of our previous labs, Newton's second law is a key component of this lab. We have the formula final velocity is equal to the initial velocity plus F net over m times delta t. Acceleration is a result of a force on the object. We know that mass is inversely proportional to acceleration in that F net is equal to mass times acceleration. Also, we know that acceleration can be denoted by the change in velocity over change in time. Using this, we're able to derive the position updating formula, which gives us the final position equaling the initial position plus V average times delta t. And in this particular lab, V average is equal to V final. There are two primary forces in this lab, Earth's gravity and drag. Earth's gravity is 9.8 meters per second, and it points downward in our particular frame of reference. It is a force of attraction between Earth and the object. Drag, on the other hand, acts in the opposite direction to gravity. It's calculated using the falling object's velocity with the force of drag equaling to negative 1/2 c rho a v squared times v hat, where p is equal to the density of air, c is equal to the coefficient of the drag force, a is equal to the surface area of the plate, and v is equal to velocity. As far as terminal velocity goes, it occurs when the magnitude of the force of drag is equal to the magnitude of the force of gravity. In our particular lab, we're going to have two stacks, one with 5 plates and one with 25 plates. In order to find using the formula from the previous slide, in order to find this, for the 5 plates, we do mg is equal to 1/2 cpa velocity squared. The magnitude of the velocity with 5 plates is equal to the root 2 mg over cpa. On the other hand, for 25 plates, using the formula from the previous slide, we get 5 times, because there's a 5 times the amount is equal to mass times gravity is equal to 1/2 cpa v squared. And in this, the velocity of 25 plates is equal to root of 10 mg over cpa. The relationship that we have is that the magnitude velocity of 25 plates is equal to root 5 times the magnitude of velocity of 5 plates. So in this lab, as time increases, so does velocity. F net is equal to 0. And when F net is equal to 0, terminal velocity has been reached. Going back to the objects analyzed, we have two items, a stack of 5 plates and a stack of 25 plates. The dimension of each plate is 0.09 meters. Also, the weight of one plate is equal to 0.0095 kilograms. This leads to 5 plates having a weight of 0.0475 kilograms and 25 plates having a weight of 0.2375 kilograms. Moving on to tracker, here we have visual images of both objects being dropped. Here we have the 25 plates, and here we have the 5 plates. As you can see, they're both dropped from the same exact point, and there's the same amount of distance between the point and the ground. As you can see, the 25 plates reached the ground at a faster speed, and we tracked the position as it fell towards the ground. The positive y was pointed upwards, negative y downwards, and we use this as our frame of reference. The data from this was later used and compared with the data from the model created in VIDLE. Moving on to VIDLE, here's the installation of our initial program. Here we set the mass for both the 25 and the 5, the positions and velocities. Here's the time step, here's the force of gravity at 9.8, here's the j hat vector for the direction of the positive y, and here's the output file for all the data that we obtained. We have the area that we determined earlier. C was a constant that we determined online from NASA, and rho was determined also by calculating the density of the air. Here is a position update for the formula. We just created the arrows in order to create the graphical representation, and then we wrote the data, and then we outputted it, the model prediction. Upon running our code, here was the graphical representation that we performed. As you can see, the 25 mass plate had a greater drag force than that of the 5 mass plate, and that the gravity acted at a greater force on the 25 than it did on the 5, at a faster rate. Here's the position versus time for the 5 plat stack, and as you can see, it was very close between the observed and the model, And the same could be said for the 25 plate stack. Putting them all together for both stacks, you can see the model did a very good job of predicting the observed data. Acceleration due to gravity results in a gravitational force acting upon an object. Earth's air creates a turbulent drag force opposite to the motion of gravity. A final terminal velocity is obtained when gravity and the drag force are equal in magnitude. The relationship that we are shown is that the magnitude of the velocity of the 25 plates is equal to square root of 5 times the magnitude of the 5 plates. The 5 stack plate predicted a time of 277 seconds, while the 25 plate stack predicted a time of 124.5 seconds. The 25 plate stack actual time was 277.4 using the derived square root of 5 in order to calculate 124 seconds. This resulted in only an error of 0.4%, which is very small. Even though this error is very small, it can be attributed to imprecise markings in Tracker due to blur, not 100% accurate calculation of drag, and movement in the x and y direction. In conclusion, this lab did an effective job of both measuring the turbulent drag on masses of two different variations and created a formula that showcased the clear relationship, denoted here by magnitude of the velocity of 25 plates is equal to the square root of 5 times the magnitude of the velocity of the 5 plates. I hope you learned a tad bit from this lab, and thank you for your time. Thank you. Bye-bye.